The definition of bundled in the National Electrical Code, specifically the 2008 edition, includes the phrase "otherwise periodically bound together." According to the interpretation, cables that are run through holes in joists are considered bundled, and consequently, they need to be derated. The primary reason for this requirement is that when cables are bundled together, they are positioned closer to one another than if they were installed separately. This proximity leads to increased heat generation within the cables. Elevated temperatures can result in insulation damage and, in more severe cases, electrical fires. To address this issue, the National Electrical Code provides derating factors for bundled cables in Table B 310.16. These factors are determined by considering the number of cables within the bundle and the type of insulation used on the cables. As an example, consider a scenario where 3 cables with XHHW insulation are bundled together. In this case, the derating factor is 0.75. This indicates that each cable can only carry 75% of its normal ampacity. It is important to note that the derating factors presented in Table B 310.16 are applicable to cables that are bundled within a raceway. If the cables are bundled outside of a raceway, the derating factors must be increased by 10% to account for the altered thermal conditions. By adhering to the derating requirements outlined in the National Electrical Code, the risk of cable overheating and subsequent fires can be significantly reduced. This practice ensures the safe and reliable operation of electrical systems, safeguarding both property and lives. Let's delve deeper into the concept of ampacity and derating. Ampacity, also known as current carrying capacity, refers to the maximum amount of electrical current, measured in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors influence a conductor's ampacity, including its size, material, insulation type, and the surrounding ambient temperature. Copper and aluminum are the most commonly used conductor materials, with copper generally having a higher ampacity for a given size due to its low electrical resistance. The type of insulation also plays a crucial role, as different insulation materials have different temperature ratings. Common insulation types include THHN, THWN, XHHW, and NUF, each with its own maximum operating temperature. The National Electrical Code provides ampacity tables, such as Table 310.15b16, which list the allowable ampacities for various conductor types and sizes based on their insulation temperature ratings and ambient temperature. These tables are essential for selecting the appropriate conductor size for a particular application to ensure safe and reliable operation. Derating, on the other hand, is the process of reducing the allowable ampacity of a conductor under certain conditions, such as when multiple conductors are bundled together, installed in high ambient temperatures, or run through conduits with limited ventilation. Derating is necessary to prevent conductors from overheating, which can lead to insulation damage, premature aging, and even electrical fires. As previously mentioned, when conductors are bundled together, they generate more heat than if they were installed separately. This is because the heat produced by each conductor is not easily dissipated, leading to a higher overall temperature. To account for this effect, the National Electrical Code provides derating factors in Table B 310.16, which reduce the allowable ampacity based on the number of current-carrying conductors in a raceway or cable. For example, if there are 4 to 6 current-carrying conductors in a raceway, the allowable ampacity must be derated to 80% of its original value. Similarly, if there are 7 to 9 current-carrying conductors, the allowable ampacity must be derated to 70%. High ambient temperatures can also significantly affect a conductor's ampacity. As the ambient temperature increases, the conductor's insulation becomes less effective at dissipating heat, leading to a higher operating temperature. To address this issue, the National Electrical Code provides correction factors in Table 310.15b2, which reduce the allowable ampacity based on the ambient temperature. For example, if the ambient temperature is higher than 30 degrees Celsius (86 degrees Fahrenheit), the allowable ampacity must be reduced according to the correction factor provided in the table. In addition to bundling and high ambient temperatures, other factors can also necessitate derating, such as voltage drop and harmonic distortion. Voltage drop occurs when the voltage at the end of a conductor is lower than the voltage at the source due to the conductor's resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, the National Electrical Code recommends limiting the voltage drop to 3% for branch circuits and 5% for feeders. Harmonic distortion, on the other hand, is the presence of non-sinusoidal waveforms in an electrical system. Harmonic currents can cause overheating of conductors and equipment, as well as interference with electronic devices. To mitigate the effects of harmonic distortion, the National Electrical Code recommends using appropriately sized conductors and equipment that are designed to withstand harmonic currents. In summary, ampacity and derating are essential concepts in electrical engineering that ensure the safe and reliable operation of electrical systems. By understanding the factors that affect ampacity and the derating requirements of the National Electrical Code, electrical professionals can select the appropriate conductors and equipment for a particular application and prevent overheating, insulation damage, and electrical fires. Let's consider specific examples to illustrate the application of these principles. Imagine a scenario where you are installing 6 current-carrying conductors of type THHN in a conduit with an ambient temperature of 35 degrees Celsius 95 degrees Fahrenheit. The conductors are size 12 American wire gauge copper, which, according to Table 310.15b16 of the National Electrical Code, has an ampacity of 30 amps at an ambient temperature of 30 degrees Celsius 86 degrees Fahrenheit. However, since there are 6 current-carrying conductors in the conduit, the allowable ampacity must be derated to 80% of its original value, as per Table B 310.16. This results in a derated ampacity of 30 amps times 0.80, which equals 24 amps. Additionally, since the ambient temperature is 35 degrees Celsius 95 degrees Fahrenheit, the allowable ampacity must be further reduced by a correction factor from Table 310.15b2. For THHN conductors with a 90 degrees Celsius rating, the correction factor for an ambient temperature of 35 degrees Celsius is 0.91. Therefore, the final derated ampacity is 24 amps times 0.91, which equals 21.84 amps. This means that each of the 6 conductors can only carry a maximum of 21.84 amps without exceeding its temperature rating. Another example could involve running cables through insulated walls or ceilings. The National Electrical Code addresses these situations as well, recognizing that insulation can impede heat dissipation and thus require derating. The specific requirements depend on the type and amount of insulation, as well as the proximity of the cables to heat sources. In these cases, it's crucial to consult the relevant sections of the National Electrical Code and manufacturer's specifications to determine the appropriate derating factors. Understanding the nuances of the National Electrical Code and applying its guidelines correctly is paramount for electrical safety. It's not simply about following a set of rules, but understanding the underlying principles and reasoning behind them. This knowledge allows for informed decision-making and ensures that electrical systems are installed and maintained in a manner that minimizes risks and promotes long-term reliability. Regular updates to the National Electrical Code reflect advancements in technology, changes in industry practices, and lessons learned from past incidents. Staying current with these updates is essential for electrical professionals to remain competent and effective in their roles. Continuing education courses, industry publications, and professional organizations are valuable resources for staying informed about the latest changes and best practices. In addition to ampacity and derating, other important considerations in electrical system design include overcurrent protection, grounding, and bonding. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from excessive current, which can cause overheating and damage. Grounding and bonding are essential for providing a low impedance path for fault current, which helps to prevent electrical shock hazards. The National Electrical Code provides detailed requirements for overcurrent protection, grounding, and bonding, which must be followed to ensure the safety of electrical systems. Furthermore, it is important to remember that the National Electrical Code is not a design manual, but rather a set of minimum safety standards. While compliance with the National Electrical Code is essential, it may not be sufficient to ensure the optimal performance and reliability of an electrical system. Good engineering practices and consideration of specific application requirements are also necessary. For example, in critical applications such as hospitals and data centers, it may be necessary to use redundant power systems and surge protection devices to ensure continuous operation and prevent downtime. The principles of ampacity, derating, overcurrent protection, grounding, and bonding are interconnected and must be considered holistically when designing and installing electrical systems. A thorough understanding of these principles, combined with adherence to the National Electrical Code and sound engineering judgment, is crucial for creating safe, reliable, and efficient electrical systems that meet the needs of the application. Let's take a moment to discuss the importance of proper documentation and labeling in electrical installations. Accurate documentation, including as-built drawings and circuit directories, is essential for troubleshooting and maintenance. Clear and concise labeling of electrical panels, circuits, and equipment helps to prevent confusion and errors, especially during emergencies. The National Electrical Code requires specific labeling requirements for various components of electrical systems, such as panel boards, disconnect switches, and control panels. These requirements are designed to ensure that electrical personnel can quickly and easily identify the purpose and function of each component. In addition to complying with the National Electrical Code labeling requirements, it is also good practice to provide additional information that may be helpful for maintenance and troubleshooting. This could include circuit breaker trip settings, conductor sizes, and equipment ratings. Laminated labels and durable marking pens are recommended to ensure that labels remain legible over time. Proper documentation and labeling not only improve the safety and efficiency of electrical systems, but also facilitate communication and collaboration among different stakeholders, such as electricians, engineers, and facility managers. In conclusion, understanding cable bundling and derating per the National Electrical Code, specifically the 2008 edition, is crucial for ensuring the safety and reliability of electrical installations. By adhering to the derating requirements and considering other factors such as ambient temperature and voltage drop, electrical professionals can prevent cable overheating, insulation damage, and electrical fires. Continuous learning and staying up to date with the latest changes in the National Electrical Code are essential for maintaining competency and providing safe and effective electrical services. The principles discussed here, combined with sound engineering practices and attention to detail, will contribute to creating robust and dependable electrical systems that meet the needs of various applications. And do not forget the importance of proper documentation and labeling in electrical installations. It is vital to keep the electrical panel documentation accurate and easily readable for all those that may need to use it. Do not rely on memory, because the job may outlast the individual that performed it. In all cases and situations, safety is of utmost concern, and it is imperative to review the NEC to confirm the local requirements. Always stay current.